Next, we'll consider a problem where we're going to calculate equilibrium concentrations of species in a reaction from the initial concentrations and the equilibrium constant. So in this case, we're going to be using the quadratic formula to solve for x. So let's consider the reaction N2O4 goes to 2NO2. And we're given a K sub C for this reaction, which is a K based on concentration of 0.36 at 100 degrees C. So this reaction mixture at 100 degrees C, which just means that our K is 0.36 because it's at that temperature, initially contains an NO2 concentration of 0.100 molar. Find the equilibrium concentrations of NO2 and N2O4 at this temperature. So we're going to get our equation into the form ax squared plus bx plus c, which is a quadratic equation, and we're going to use the quadratic formula to solve for x. The quadratic formula is x is equal to minus b plus or minus the square root of b squared minus 4ac all over 2a. We're also going to use this property. We know that if we have a term, a plus b, all raised to the second power, then we can solve that by saying a squared, our first part of the term, plus 2 times a, which is the first term in the parentheses, times b, which is the second term in the parentheses, plus b squared. Okay, so this is the way we solve a square like this. So we're going to be using that property as well. Okay, so let's go ahead and get started. The first thing we need to do is write our reaction down, and we'll look at an ICE table and see if we need to solve for Q. Okay, so our reaction is N2O4 goes to 2NO2. Okay, and so if we make an ICE table, so to make an ICE table, we make a vertical line to the left of the reaction and then a horizontal line under the reaction, and write the abbreviation ICE, which stands for initial, change, and equilibrium. We'll put a double line between starting materials and products, and if we have more than one of each, we will put a single line between them. Okay, so let me clean this up a little bit. Okay, so our starting concentrations for the N2O4 was 0, because we were told that we initially only had NO2 of 0.1 molar, so our NO2 is 0.100 molar. Okay, that means we have no N2O4. So we don't need to calculate Q in this case, because if we only have products, and this is a reversible reaction, it can only go towards starting materials. So you could calculate Q if you wanted to. It's set up the same way as K, but we don't need to because we have no starting materials in this case. Okay, so let's go ahead and set up our K expression. So we're going to say that K, so we're going to say that K is equal to NO2 squared over N2O4. So what we need to do is find these equilibrium values that we're going to plug in here by filling out our ICE table. Okay, so if we have only products and no reactants in the beginning, then we're going to have to be losing products and gaining reactants. So we're going to be gaining X of the N2O4 because it has a 1 as a coefficient of the reaction, and losing 2x of the NO2 because it has a 2 as the coefficient of the reaction. Okay, so at equilibrium for our NO2, we're going to have 0.100 minus 2x because we're losing 2x, and for the N2O4 we'll have 0 plus x, so we just have x. Okay, so what we have to do is take then these equilibrium values, which we just found from our ICE table. We're going to take the equilibrium values and plug them into K and then solve for x. Okay, so in this case we're going to say K sub C equals NO2 squared over N2O4, and I'm only writing it down here so that it won't be so messy. Okay, so we're going to plug in the equilibrium values. So K sub C is equal to 0.100 minus 2x over squared over x. Okay, and we're going to set that equal to 0.36 because that was our K. Okay, so now in order to solve this part, this term right here, in order to figure out that square, we're going to use this property. A plus b squared is equal to a squared plus 2ab plus b squared. In fact, I think I'll write that here. A plus b squared is equal to a squared plus 2ab plus b squared. Okay, so let's just go ahead and solve that numerator. Okay, so we're going to say 0.36 equals, and our a is 0.100, so 0.100 squared is 0.0100. Alright, and then we have plus 2 times a times b. Okay, so we have, so we're going to have plus, and then 2 times a, which is 0.100, times b, which is minus 2x, alright, plus b squared, which is, I don't know why it keeps doing that, negative 2x squared. Okay, when we work all this out, we get 0.36 equals 0.0100 minus, because we have this negative here, 0.400x, and then the square gets rid of the negative on the end, so we have plus 4x squared. Okay, so we're not quite in the form of a quadratic. Okay, so we need to get in this form, ax squared plus bx plus c equals 0, and then we can plug into the quadratic formula. So let's go ahead and write that down. We want to get into the form, let me put that here, ax squared plus bx plus c equals 0. Okay, so let's go ahead and do that. So what we're going to do is put my 4x on the left. Okay, so if I do that, if I say 4x squared, so basically I'm going to have to change the sign on everything, because if I move the 4x squared to the left, I'm going to be changing the sign. So I end up with 4x squared minus 0.76x plus 0.0100 equals 0. So I combined like term and moved the 0 to the, got the 0 on the right and all the other terms on the left. Okay, so now I'm going to plug that into the quadratic equation, where I have x equals minus b plus or minus the square root of b squared minus 4ac all over 2a. Okay, so alright, and this is my a in this case, and this is my b, okay, and this is my c. So I want to plug all of that into the quadratic formula, and I get x equals minus negative 0.76, okay, plus or minus the square root of negative 0.76 squared, okay, minus 4 times 4 times c is 0.0100, okay, all over 2 times 4. Okay, so here is a, here was b, and here was c. Alright, so let's go ahead and work this out. We get x equals 0.76 plus or minus 0.65. Clean that up a little bit. .65, okay, divided by 2 times 4 is 8. Okay, so we get x equals 0.176 and x equals 0.014. Well, obviously we can't have two different concentrations. So let's go ahead and examine these further and see which one applies. Okay? So we see that if we go back to our previous ice table, we see that our N2O4 concentration equals X, and our NO2 concentration is 0.100 minus 2X. Okay? So the NO2 concentration is 0.100 minus 2X, and the N2O4 concentration is equal to X. So if X is 0.176, then we're going to have our NO2 concentration equal to 0.100 minus 2X, so that's equal to 0.100 minus 2 times 0.176, so that will give us negative 0.252. So we can't have a negative concentration. Okay, so because of that, that throws out this value. So this value is not valid, so our X equals 0.176 is not valid. So we can use X equals 0.014 and see what we get. So if X equals 0.014, our NO2 concentration at equilibrium is equal to 0.100 minus 2X, which is equal to 0.100 minus 2 times 0.014. That's equal to 0.072 molar. Okay? And N2O4 concentration is equal to X equals 0.014 molar. Okay, so that's how we find our equilibrium values using the ice table and the K. Okay, so we can verify that we got the right answer because our K sub C is equal to NO2 squared over, clean that up a little bit, NO2 squared over N2O4, so that's equal to 0.072 squared over 0.014, so that's equal to 0.37, which is close to the expected value of K, which was 0.36, so we got the answer we expected. So that's how we solve this kind of problem. So we'll work another one in the next video.